In this video, we are going to review integration by parts, one of the most important mathematical steps used in the boundary element method. I will explain this concept using simple one-dimensional examples so you can clearly see where it comes from and why it is important. We will look at how integration by parts is derived from the product rule of differentiation and understand its meaning step by step. This will build the foundation we need before applying it to differential equations in future videos. Let's start with the product rule of differentiation. The derivative of wv with respect to x is d over dx wv equals dw over dx times v plus w times dv over dx. Now if we arrange this equation, we can isolate term w dv over dx and it becomes w dv over dx equals to d over dx wv minus dw over dx times v. Next, we integrate both sides with respect to x. On the right hand side, the first term, I mean this one, becomes the integral of a total derivative, which can be directly written as wv. So we get integral of wv prime equals wv minus integral of v w prime dx. We also missed a dx here. This is the integration by parts formula. It allows us to transfer the derivative from one function to the other. Finally, if we apply the limits a and b, we get the definite form as this: integral from a to b of w times v prime equals to wv from a to b minus integral from a to b v w prime. This is the equation we will use later when deriving the weak form and the boundary integral equations in boundary element method. Now let's apply integration by parts to a second order derivative. We start with this integral from a to b w d2u over dx2, and to make it easier, we assume that dw over dx is v. Substituting this into the equation, we will have the original integral equal to this one. Now, using the integration by parts formula from the previous slide, this becomes minus integral from a to b v dw over dx times dx plus wb vb minus wa va. Replacing back v with du over dx, we will get equation A, as you can see here. So this is basically this one. We just replaced v with its original value du over dx, as you can see in these expressions. The next one, I mean the box B, is simply a rearranged version of the same expression, and both are equivalent and will be used later for illustration. So the key idea here is that integration by parts reduces the derivative order and introduces the endpoint terms at x equal to a and x equal to b. So here we have d2u over dx2, but when we use integration by parts, this would be du over dx, and one of the derivatives will be transferred to w. And then you can also see the endpoint terms at x equal to a and also x equal to b. Now let's extend the same idea to a fourth order derivative. So we start with this integral w d4u over dx4, and similar to before, we can define v equals to d2u over dx2, and if you substitute this one in the main integral, we need to handle this integral from a to b w d2v over dx2 times dx. Now we can directly use the results from equations a and b from the previous slide. So using equation a, as you can see here, I can write this integral as this equation And using equation B, which was the rearrangement of equation A, I can just write this term here as this one. So if I replace this one here, I will have the main integral would be equal to integral of v d2w over dx2 from a to b plus va dw over dx at x equal to a minus vb dw over dx at x equal to b plus wb times dv over dx at x equal to b minus wa dv over dx at x equal to a. Now I just replace back v with its original value d2u over dx2 in this equation. Then I will get the final answer which I am looking for, which is integral of w d4u over dx4 is equal to integral from a to b d2u over dx2 times d2w over dx2 dx, and then you will see the boundary terms at x equal to a and x equal to b. So you're gonna have d2u over dx2 times dw over dx at x equal to a minus d2u over dx2 times dw over dx at x equal to b plus wb times d3u over dx3 at x equal to b minus wa times d3u over dx3 at x equal to a. So you can see that integration by parts reduces the derivative for u up to 2 times and transfers the derivation reduces the derivative for u up to 2 times and then transfers the derivation to the w function. So instead of w d4u over dx4, we are gonna have d2u over dx2 times d2w over dx2, and we are gonna have all of the values related to the boundaries. Since this is a 1D problem, boundaries are points at x equal to a and x equal to b.